Chapter 3. Symmetry and Pattern. Reflection symmetry or line symmetry. A figure is said to be symmetric when it can be folded and matched. Reflection symmetry, sometimes called line symmetry or mirror symmetry, is easy to recognize because one half is the reflection of the other half. Line of symmetry. Here the face of the dog has been made perfectly symmetrical. The dotted line drawn on the center is called the line of symmetry. Now look at this beautiful butterfly. It is folded in two halves. See that its two halves match exactly. This particular line created by folding the butterfly is called the line of symmetry or the line of reflection. When the butterfly is folded at the line of symmetry such that the two sides match each other exactly, then we can say the two sides are congruent and the butterfly is symmetrical. Let us draw the line of symmetry in the following figures. Horizontal line of symmetry, vertical line of symmetry, diagonal line of symmetry. Many shapes also have multiple lines of symmetry or no line of symmetry. 1. The figure has 4 lines of symmetry. 2. The figure has 2 lines of symmetry. 3. The figure has no line of symmetry. Symmetric objects around us. Now we will see some examples of symmetric objects around us, that is, the letters of English alphabets, traffic signs, geometric shapes, and the other images. Symmetry exists in architecture all around the world. The best known example of this is the Taj Mahal. Line symmetry can also be seen in the letters of English alphabets. The capital letter B given alongside has only one horizontal line symmetry. If we fold this B from the horizontal line, its top and bottom parts match each other exactly. But the letter B does not have vertical line symmetry. When we draw a line vertically, the left and right parts of B do not match each other exactly. The capital letter P given below has no line symmetry. Look at a few letters of the English alphabets. A. Vertical axis of symmetry. B. Horizontal axis of symmetry. O. Both axes of symmetry. J. No axis of symmetry. Let us try to make a word using letters with vertical axis of symmetry. Let us now make a word using letters with horizontal axis of symmetry. Figures with more than 2 lines of symmetry. Look at the below given figures. You will observe more than 2 lines of symmetry. 1 line of symmetry, 1 line of symmetry, 2 lines of symmetry, 2 lines of symmetry, 3 lines of symmetry, 4 lines of symmetry. A circle has infinite lines of symmetry. When a figure is symmetrical, the other half of the figure can be drawn by looking at the given half. Slides, flips, and turns. Slide. A slide takes place when a shape moves in one direction from one place to another. Flip. A flip takes place when a shape is flipped across a line and faces the opposite direction. Turn. A turn takes place when a shape is turned through an angle. Original position. 1. Draw a tessellation with pentagons or hexagons. 2. Draw a tessellation by combining two plane shapes. 3. Write the letters D, P, M, Y, and Z and read their image through a mirror. How does each letter look like? Original position. Identification of patterns in square and triangular numbers. Patterns often occur in science and mathematics. They are found by groups of shapes, objects, diagrams, or numbers. Patterns are the part of daily life and are very useful in mathematics as they can help us to solve some problems. Patterns in square numbers. A square number is a number that can be arranged in a square pattern. The patterns of the first 3 square numbers are depicted below. The first square number 1 is shown as a square containing a single dot. There is one row containing one dot. So there is 1 into 1 is equal to 1 dot in this square number. The second square number 4 is shown as a square with 2 dots in each side. It is clear that there are 2 rows each containing 2 dots. So there are 2 into 2 is equal to 4 dots in this square number. The third square number 9 is shown as a square with 3 dots in each side. It is clear that there are 3 rows each containing 3 dots. So there are 3 into 3 is equal to 9 dots in this square number. From the above discussion, we can make a series of square numbers 1, 4, 9, 16, 25, 36, 49 and so on. Observing the above patterns, we find that a square number is made by squaring it where it is in a pattern. For example, the second number is 2 squared, that is 2 into 2 is equal to 4. The eighth number 8 is squared, that is 8 into 8 is equal to 64. Patterns in triangular numbers. Triangular numbers are those numbers which can be formed by counting the number of objects used in making a triangle. Look at the following for other triangular patterns. From the above discussion, we can make a series of triangular numbers 1, 3, 6, 10, 15, 21, 28, 36 and so on. Pascal's triangle. One of the most interesting number pattern is Pascal's triangle, named on Blaise Pascal, a famous French mathematician and philosopher. To build the triangle, start with 1 at the top, then continue placing numbers below it in a triangular pattern. Each number is just the 2 numbers above it added together. Observations based on Pascal's triangle. Diagonals. Of course, the first diagonal is just ones and the second diagonal has the counting numbers, that is 1, 2, 3, 4, 5, etc. The third diagonal has the triangular numbers, that is 1, 3, 6, 10, 15, etc. The fourth diagonal, not highlighted, has the tetrahedral numbers, that is 1, 4, 10, 20, 35, etc. Horizontal sum. What do you notice about the horizontal sums? Is there a pattern? Isn't it amazing? It doubles each time. Sierpinski triangle. An ever-repeating pattern of triangles. Let us learn how we can create a Sierpinski triangle. Step 1. Start with a triangle. Step 2. Shrink the triangle to half and put a copy in each of the 3 corners. Step 3. Repeat step 2 for the smaller triangles again and again forever. First 5 steps in an infinite process. We can use any shape. Make your own number patterns. You can make your own number patterns using coins or matchsticks. Here is an example using coins. Size is equal to 1, 1 coin. Size is equal to 2, 6 coins. Size is equal to 3, 15 coins. Size is equal to 4, 28 coins. How many coins would you need when size is 5? Can you make a formula that will tell you how many coins are needed for any size? The formula may look something like coins is equal to size into size plus dash. Example 1. In a series of square numbers, find the square number next to 1, 121 to 400. Solution 1. Since 121 is equal to 11 into 11, the number next to 121 is 12 into 12 is equal to 144. 2. Since 400 is equal to 20 into 20, the number next to 400 is 21 into 21 is equal to 441. Example 2. In a series of square numbers, find the square number just before 1, 625 to 196. Solution 1. Since 625 is equal to 25 into 25, the number just before 625 is 24 into 24 is equal to 576. 2. Since 196 is equal to 14 into 14, the number just before 196 is 13 into 13 is equal to 169. Example 3. With the help of 15 dots, create a triangular pattern. Solution. We create a triangular pattern using 15 dots as shown alongside. Example 4. What is next triangular number? 28, 36. Solution. Difference between 36 and 28 is equal to 36 minus 28 is equal to 8. Therefore, the next triangular number is 36 plus 9 is equal to 45. Remember, each side of the triangle has 5 dots. Example 5. What smallest number should be added to 396 to make it a square number? Solution. We have 19 into 19 is equal to 361 is less than 396. 20 into 20 is equal to 400 is greater than 396. Since 400 minus 396 is equal to 4 and 396 plus 4 is equal to 400, therefore 4 should be added to 396 to make it 400, 20 into 20, which is a square number. Example 6. Which of the following numbers are square numbers? 11, 12, 16, 32, 36, 49, 56, 81, 121. Solution. Numbers 16, 4 into 4, 36, 6 into 6, 49, 7 into 7, 81, 9 into 9, and 121, 11 into 11 are the square relation in the sequence of odd numbers between consecutive square numbers. Square numbers have several interesting properties. Let us see the following patterns for various properties. Pattern A, 1 into 1 is equal to 1 is equal to 1. The first odd number is 1. 2 into 2 is equal to 4 is equal to 1 plus 3. Sum of first two odd numbers. 3 into 3 is equal to 9 is equal to 1 plus 3 plus 5. Sum of first three odd numbers. 4 into 4 is equal to 16 is equal to 1 plus 3 plus 5 plus 7. Sum of first four odd numbers. 5 into 5 is equal to 25 is equal to 1 plus 3 plus 5 plus 7 plus 9. Sum of first five odd numbers. By observing the above pattern, we can conclude that the square number formed by n into n is equal to sum of the first n odd numbers. Pattern B. 1 is equal to 1 is equal to 1 into 1. 1 plus 3 is equal to 4 is equal to 2 into 2. 4 plus 5 is equal to 9 is equal to 3 into 3. 9 plus 7 is equal to 16 is equal to 4 into 4. 16 plus 9 is equal to 25 is equal to 5 into 5. 25 plus 11 is equal to 36 is equal to 6 into 6. 6 into 6. 36 plus 13 is equal to 49 is equal to 7 into 7. The above pattern can be represented pictorially as follows. Pattern C. Look at the following pattern which relates a square number with another square number just before it. 7 into 7 minus 2 into 7 minus 1 is equal to 6 into 6. 6 into 6 minus 2 into 6 minus 1 is equal to 5 into 5. 5 into 5 minus 2 into 5 minus 1 is equal to 4 into 4. Can you extend this pattern further? Pattern D. See the following pattern carefully and write 3 more such relations between square numbers. 3 into 3 plus 2 into 3 plus 1 is equal to 4 into 4. 4 into 4 plus 2 into 4 plus 1 is equal to 5 into 5. 5 into 5 plus 2 into 5 plus 1 is equal to 6 into 6. 6 into 6 plus 2 into 6 plus 1 is equal to 7 into 7. Example 8. Express the following square numbers as the sum of odd numbers. 1, 49, 2, 81. Solution. 1. Since 49 is equal to 7 into 7, therefore 49 can be expressed as the sum of first 7 odd numbers. Hence, 49 is equal to 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13. 2. Since 81 is equal to 9 into 9, therefore 81 can be expressed as the sum of first 9 odd numbers. Hence, 81 is equal to 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17. Example 9. Without actual addition, find the following sum. 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus 19 plus 21. Solution. Given sum is the sum of the first 11 odd numbers. Therefore, 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17 plus 19 plus 21 is equal to 11 into 11 is equal to 120.